10 years, 85 orbital passes, and it still took scientists more than 2 years to understand what one spacecraft had already recorded. That delay is the story most people miss. NASA had the numbers, NASA didn't have the answer. And when the answer finally arrived in July 2026, it forced a rewrite of what scientists thought they understood about the moons of Jupiter. Here's the question worth sitting with. If we've been staring at these 4 moons since Galileo first spotted them in 1610, how is anything about them still a mystery? The honest answer is uncomfortable. We've been looking at their surfaces for centuries. We've barely started looking underneath. That changed with Jupiter's most violent moon, Io. NASA's Juno spacecraft made 2 close passes near Io in December 2023 and February 2024, coming within roughly 930 miles of its surface. During those flybys, Juno aimed its microwave radiometer instrument at Io, probing 6 to 20 feet beneath the surface. Depth nobody had directly measured before. What came back should unsettle anyone who thought this moon was already understood. Everywhere the instrument looked, temperatures rose more than 40 degrees Fahrenheit within just a few feet of the surface, a gradient far too steep for sunlight to explain. Read that again. 40 degrees within feet, on a moon already famous for hundreds of active volcanoes, simmering lava lakes and sulfur plumes, blasting hundreds of kilometers into space. Scientists always assumed tidal heating. The gravitational squeeze from Jupiter and neighboring moons was driving Io's fury. What they never had, until now, was direct proof of what that heat actually looks like just beneath the surface. This is the difference between a theory and a measurement, and the measurement came back stranger and more violent than the theory predicted. But here's where it escalates past one angry little moon. According to the researchers behind the discovery, the same tidal heating mechanism driving Io's extreme volcanism is believed to also power the hidden oceans beneath the icy shells of Europa and Ganymede. Stop and think about what that means. The exact force ripping Io apart from the inside may be the very thing keeping liquid water alive on 2 neighboring moons, oceans that might otherwise have frozen solid billions of years ago. One invisible gravitational engine, 3 radically different results. Fire on one moon, frozen oceans, kept liquid on 2 others. That's not the only surprise buried in Io's data. Before this, Io was known mainly for towering mountains and violent terrain, but the new readings revealed that much of its surface is unexpectedly smooth, with flat plains stretching 60 miles or more, compared by researchers to the Great Plains back on Earth. A moon defined by chaos, quietly hiding, stretches of calm nobody predicted. Nobody has explained why yet. And a separate earlier discovery adds another layer. A December 2024 paper, using gravity data from those same flybys, found Io's volcanoes are powered by individual magma chambers rather than one connected global sea of molten rock beneath the surface, as many scientists had assumed. That single correction changes how researchers model tidal heating everywhere. It means the process doesn't necessarily create uniform interior conditions. It can fracture a moon's insides into scattered, unpredictable pockets of extreme heat. These Io findings were only published July 22, 2026, in the Journal of Geophysical Research. Planets, days before this was written. Not old news, not a recycled headline. A live discovery still being absorbed by the scientific community as you're reading this. Now widen the frame, because Io was never the main event. The real target has always been Europa. NASA's Europa Clipper, the largest spacecraft the agency has ever built for a planetary mission, launched October 14, 2024, aboard a SpaceX Falcon Heavy rocket. It is currently mid-flight, deep into a journey that will eventually cover 1.8 billion miles. To make that journey possible, Clipper is using a sequence of gravity assists, borrowing momentum from planets instead of burning impossible amounts of fuel. It swung past Mars in February 2025 to adjust its trajectory, and it's now approaching its final gravity assist, a flyby of Earth in December 2026, this December, before being slingshotted out toward Jupiter. As it arrives, it will slip past Ganymede itself, using that moon's gravity to help settle into orbit around Jupiter, currently projected for April 2030. Here's the detail that should genuinely concern you. Recent analysis revealed Europa Clipper's hardened electronics may be more vulnerable to Jupiter's radiation than engineers originally expected, a discovery made after launch, after the spacecraft had already committed to its billion-mile trajectory with no possibility of repair. And that radiation is not a minor obstacle. Jupiter is surrounded by a magnetic field 20,000 times stronger than Earth's, trapping radiation belts intense enough to degrade spacecraft electronics with every single pass through them. Once Clipper finally arrives, it will orbit Jupiter and conduct 49 close flybys of Europa, running 9 science instruments simultaneously on every pass, 49 separate chances for hardware already flagged as vulnerable to fail, and 49 separate chances to finally answer the question this entire mission exists for. That question, what's actually underneath Europa's ice? Scientists believe a saltwater ocean exists beneath Europa's crust, potentially holding more than twice as much liquid water as all of Earth's oceans combined. Twice the water of every ocean on our entire planet, sealed beneath ice on a moon smaller than our own. Evidence already suggests Europa may host organic compounds and energy sources beneath its surface, water, chemistry, and energy together. All the three ingredients astrobiologists consider the baseline requirements for life. And, according to NASA's own mission scientists, the stakes reach far beyond one moon. If Europa turns out to be habitable, it may mean there are more habitable worlds in our solar system and beyond than previously imagined. Not just another moon, a statistical shift in how many places in the universe might be capable of holding life at all. Europa isn't hiding this story alone either. Ganymede, the largest moon in the entire solar system, bigger than the planet Mercury, has been generating a mystery of its own. Recent observations show auroras on Ganymede that resemble Earth's own northern lights, while Jupiter's moons more broadly leave cold footprints behind in Jupiter's own auroras, detected using the James Webb Space Telescope. Ganymede is the only moon in the entire solar system known to generate its own internal magnetic field. Not borrowed from Jupiter, but self-produced, the same basic mechanism that powers Earth's field from deep within our planet's molten core. A magnetic field like that usually means one thing: something is moving beneath the surface. And given what Juno has now confirmed about tidal heating maintaining hidden oceans on icy moons, Ganymede's aurora may be a visible signature of exactly that. An active, energetic interior, not a dead frozen shell. Connect all three moons, and the picture stops looking like three separate discoveries and starts looking like one unfolding story. Io's measured subsurface heat is physical proof of the tidal mechanism scientists believe sustains Europa's ocean. Ganymede's magnetic field and aurora may be direct evidence of a similar hidden sea beneath its own ice. Europa's chemistry, its organics, its energy sources, may be the final ingredient astrobiologists have been waiting years to confirm. Every discovery reinforces the next. Every moon is a different chapter of the same underlying process. And this campaign doesn't stop at Jupiter. According to Johns Hopkins Applied Physics Laboratory, the same scientist leading one of Europa Clipper's camera teams is simultaneously leading NASA's Dragonfly mission to Saturn's moon Titan, currently slated to launch no earlier than 2028. The same minds mapping Europa's chaotic ice are already preparing humanity's next journey to an entirely different ocean world, around an entirely different planet. This isn't a single mission, it's an accelerating pattern, moon by moon, hidden ocean by hidden ocean. There's a historical weight sitting under all of this that's easy to miss. These four moons, Io, Europa, Ganymede, and Callisto, were first observed by Galileo Galilei in 1610 through a homemade telescope when he initially mistook them for distant stars before realizing they orbited Jupiter itself. That discovery directly undermined the era's dominant belief that Earth sat at the center of the universe. 400 years later, humanity is pointing new instruments at those same four moons, and the discoveries emerging from them are once again quietly dismantling an assumption we didn't realize we were still making. This time, not about the structure of the cosmos, but about where in it life might actually be capable of existing. Nobody is willing to say that word outright yet. Not NASA, not the researchers who spent 2 years decoding a single pair of Io flybys, not the engineers who only recently discovered their own spacecraft might be more fragile than they thought. That hesitation isn't a lack of confidence. It's caution from people who know the difference between a promising signal and a confirmed answer, and who refuse to blur that line even when the signals keep stacking up in the same direction. Moon after moon, instrument after instrument, over more than a decade of data. But here's what nobody can control. Europa Clipper still has to survive its final Earth flyby this December. It still has to thread a precise path past Ganymede's gravity in 2030. Its potentially vulnerable electronics still have to withstand a radiation field 20,000 times stronger than the one protecting our own planet, across 49 separate encounters with the very ocean it was built to study. Juno, already a decade into a mission designed for far less punishment, has to keep functioning long enough to finish handing over whatever else is buried in its accumulated data. Data that took over 2 years just to properly interpret from a single pair of passes. Somewhere between now and 2030, beneath a shell of ice on a moon smaller than our own, there may be twice the water of every ocean on Earth, sitting in absolute darkness, waiting to either confirm the biggest question in modern astrobiology or rule it out entirely. Nobody knows yet which outcome we're racing toward. All anyone can say for certain is that the spacecraft carrying the answer is already in motion, gathering speed somewhere between Mars and its next brush with Earth, carrying instruments that may or may not survive long enough to find out what's actually down there.